How can we build a self-determined reciprocal recommender system with strong privacy guarantees? Hello, my name is Saskia Nuñez, and I'm pleased to present our joint work to provide a concept of how such a system could look like. In order to motivate a self-determined recommender system, we use a job marketplace as running example. So let us assume Alice is looking for a job. The marketplace is a platform to connect candidates with recruiters. Usually, job recommender systems are implemented as centralized platforms. In other words, in order to receive recommendations, Alice needs to disclose a significant amount of personal data like her skills and past jobs to create a user profile which is collected and stored on a central server. Content-based recommendations are generated on the server by calculating the similarity between Alice's profile and a job profile. This approach poses a serious threat to users' data control and is therefore not self-determined. To be honest, Alice would like to keep her data local and not share it until she applies for a job. So, what can we offer her? Alice could derive personalized recommendations locally without disclosing her profile. She downloads the job profile and compares it to her own profile. Both job profiles and candidate profiles are based on keywords extracted from job requirements and candidate skills respectively. To reduce the computation complexity, the set of keywords can be represented as a binary vector. However, since the vector can become very large, we propose to use a Bloom filter to represent the profiles and thus keep the memory footprint small. A Bloom filter is a probabilistic data structure which consists of a bit array of a fixed length with all values initialized to 0 and using different hash functions to add keywords. So the hash function takes a keyword as an input and determines a position in the bit array that is accordingly set to 1. So assume, for example, Alice has the keyword statistics in Python. These keywords are hashed and the corresponding bits are set to 1. Job requirements are mapped to Bloom filters in the same way. Now, Alice can download the Bloom filter of the job offer and she can calculate the cosine similarity locally. This way, she can compare the similarity for each downloaded job and find jobs that match her profile without having to share her data. Well, recruiters also have an interest in finding suitable candidates. But to get the best end candidates, a recruiter needs the candidate profiles that do not want to be shared due to privacy concerns. The false positive rate of a Bloom filter provides some uncertainty. For example, in Alice Bloom filter, a hash value of statistics and Python are both mapped to the same bit, the last bit. However, it is unable to guarantee strong privacy, like differential privacy. For example, an attacker can still determine that a profile does not contain certain keywords by inspecting the bits set to 0. To guarantee differential privacy, we use BLIP, Bloom filter, then flip. It's an approach where a Bloom filter is combined with the randomized response technique. With the probability, the bit of the Bloom filter is flipped, that means a 1 changes to 0 and a 0 to 1. Otherwise, the bit does not change and remains the same. The recruiter then receives the flipped Bloom filter from which she cannot derive Alice's skills, as it remains unclear whether a set bit is a result of randomization or truly corresponds to a certain keyword. But she can still determine the cosine similarity by correcting the scalar product of the Bloom filters with known probability. Differential privacy is then guaranteed depending on the probability and the number of used hash functions. So let's summarize what we have. We have several candidates with their Bloom filter and flipped Bloom filters, and recruiters with the Bloom filters for their job offers. Recruiters can send the Bloom filter of a job offer to candidates who can then locally determine the similarity and decide whether to apply to the job. The candidates in turn can send their flipped Bloom filter to the recruiters so that they can identify top candidates and contact suitable candidates. Recruiters and candidates effectively build a peer-to-peer network. In a naive approach, the peer-to-peer network must be synchronous to allow direct exchange between recruiters and candidates. Since candidates can go offline unexpectedly, we propose to use the interplanetary file system, shown IPFS, as a distributed storage layer. IPFS is a data network that allows us to distribute candidate and job profiles asynchronously without the introduction of a central server. Using IPFS faces three main challenges. First, ensuring profile availability. In order to ensure asynchronous availability, candidate and job profiles needs to be actively replicated. Second, job and candidate profile discovery can be ensured by utilizing the publish-subscribed architecture to announce content identifiers of the candidate or job profiles. And for new candidates, we maintain a list of content identifiers. And third, in order to ensure access control, that means control over who reads the profile, we suggest encrypting candidate profiles and sharing the decryption key only with selected recruiters. For detailed discussion of how to address the challenges, I refer you to our paper. In our work, we evaluated the privacy utility trade-off of computing the similarities with Bloom filter and flip Bloom filter. We used a real dataset of the employment website Career Builder, which contains job offers, candidates, and their application history. We randomly select some job offers from which we extract keywords, which we map to the Bloom filter. On the one hand, we have the candidate profile, which consists of the Bloom filter or flip Bloom filter of their applied jobs. On the other hand, we have new job offers, jobs that none of the candidates have in their application history. For each job offer, we identified the 20 candidates with highest similarity scores from all candidates. And as utility metric, we use precision at 20 and average precision. We compared the recommendation based on the Bloom filter with and without differential privacy guarantee with a binary vector model. So in other words, the recommendation made by the binary vector represents our ground truth. A precision of 50% means that 10 out of the 20 recommended candidates are the same as when they are recommended with the binary vector. An average precision of 1 indicates that all relevant candidates are at the first positions. For the Bloom filter, the length and the number of hash functions must be specified. Therefore, we plotted the mean precision at 20 with number of hash functions on the x-axis and varying values for the length. The results generally indicate that a longer Bloom filter leads to more utility, and with more hash function, the precision decreases. We obtained the highest precision with 1 hash function and a Bloom filter of length 4096, which corresponds to the length of the binary vector. Therefore, for our next experiment, we use these parameter values. To evaluate the privacy utility trade-off, we first plot the utility of the Bloom filter model. That means the candidate profiles are not flipped and we do not guarantee differential privacy. It provides almost the same accuracy as the binary vector. But since the Bloom filter already provides certain deniability due to bit collisions, we recommend using a Bloom filter instead of a binary vector. Then we plot the utility of the flip Bloom filter. That means that a recruiter obtains the candidate's flip Bloom filter. The precision at 20, as well as the average precision of the flip Bloom filter, increases with higher epsilon. For small epsilon, ln3, the average precision is 0.75. That means a high proportion of relevant candidates appear early in the recommendation list. In our evaluation, we assumed the same privacy guarantee for each candidate. However, with our approach, it is also possible that each candidate chooses their own desired privacy guarantee to be more flexible. Let me sum up. We use Bloom filters to allow local computation of recommendations for a self-determined system. By flipping the Bloom filter, we guarantee strong privacy, more precisely differential privacy. And utilizing IPFS, we allow a two-sided asynchronous exchange of data, increasing users' control over the data in a distributed network. If you have any further questions, I'm happy to answer them after the talk or via email.